eigenproblem, okay, with eigenvalues, eigenfunctions, A dagger psi n. All right, and then let's look at the eigenvalues. The eigenvalues equal En plus h bar omega. All right, this is the big kicker. What wave functions are En's the eigenvalues of? Okay, how about this? En is the eigenvalue of psi n. So this is the eigenvalue of psi n. Right? And now, what is h bar omega? Well, let's look at h bar omega. H bar omega is h over 2 pi times omega is 2 pi over the period. All right, which equals, those cancel, so it's h times 1 over period, which is h times frequency. So this equals h times frequency.
Oh, that's cool. Get back to your energy.
And what is it?
It's the energy.
Say, I need one more word.
Maybe absolute energy?
It's the chunk of energy, but the word I'm really working for is not the chunk, it's the quanta of energy. So, this eigenvalue, this new eigenvalue, is the original eigenvalue, the eigenenergy, plus how much?
The n quanta.
One new chunk of quantum energy, of quantized energy. So in other words, how can we maybe interpret this? We've got this new wave function right here that we built from psi n, with the eigenvalue that we got being the eigenenergy for psi n plus 1.
So it would be n plus 1.
That's it. Alright, so in other words, this operator, A dagger plus, acting on psi n, creates what new eigenfunction? That has energy, En plus 1. Well, one new chunk of quanta. So this becomes which one?
Psi n.
Psi n plus 1. Alright, so let's rewrite it. So we can write it as En plus h bar omega times psi n plus 1 equals E plus times psi n plus 1. And now, is that correct?
You want to get back to the Hamiltonian, don't you?
Well, we've got what we want. We've got this operator, the raising operator acting on our wave function, raises it to the next highest, basis set, the next highest stationary state. We're looking at stationary states. And what's the energy of the next highest stationary state? It has one more quanta of energy.
Is it E total? What's it, E?
E plus.
N plus 1.
N plus 1 if you want. N plus 1. Yeah. This is an argument you're going to have to go through. Trust me, take out a piece of paper and just follow this all, with your notebook right there, and do it right by this side, and do it and ask yourself, do I understand why I'm taking each step, and do I understand each conclusion? Alright? But in the end, you conclude the following, that A dagger plus psi n equals what? What does this operator then do to this? And the discussion that we just had.
Increases that
This
energy.
is the next. Raise it to the next energy.
It raises it to the not. It's not so
stationary
much about
state.
the energy. It gives us the next
Stationary state.
stationary state. So it gives us psi n plus 1. So again, what we showed is that working all through this algebra, it's very nice, is that we end up with an eigenvalue problem, where that eigenvalue problem looks like it has an eigenfunction. That eigenfunction was built from the nth state, where the eigenvalue of this new eigenfunction is the nth state energy plus one more quanta of energy. And therefore we interpret that original eigenfunction as the next highest state that would give us, that would correspond to the energy of En plus 1. Alright, so this is tough. And you really got to go through this. But it's super important. Okay, so now why do I call these raising and lowering operators?
Because they raise and lower to the next state.
Okay, so we just showed that it raises to the next level, alright? But then what do you think this one does?
Lowers, so that's stable.
So what do you think the
Psi
way
n minus 1.
it builds psi n minus 1? Alright, now the goal of all this was to solve for the separable solutions, for the harmonic oscillator potential, right? And have we solved for them yet?
No.
No. So this is all in our repertoire of tricks, these raising and lowering operations. Alright, so now, with all this as a tool, we'll now actually go and we'll solve for some eigenfunctions. Everybody got the picture? Alright, so what we've done is we've introduced raising and lower operator as it's a bag of tricks that we now have, and we're going to now solve for the harmonic oscillator potential. Okay. Actually, let me leave that. Alright, so that is just very tricky stuff, guys, but when you get it, you'll smile. Alright, so work through it as many times as you have to work through it until you get it. Alright, this is all good stuff. Okay, so now here's the argument. We want to solve the harmonic oscillator. So this is the time independent, the separable solutions. We want to solve for, what are these called? They're the separable solutions to the time independent Schrodinger's equations, right? They're the stationary states because we did separation of variables. They're going to be stationary because we pull the time dependence out in the separation of variables. All right? So these are the stationary states of the harmonic oscillator. So our goal, of course, is to solve for the stationary states of the harmonic oscillator. And let's see, what did I H bar?
So there's separable solutions too?
So the only technique that we've done is to get to here. What do you really solve? You solve Schrodinger's time-dependent equation, right? So to get to here, what did we have to do? Separation of variables. So our whole technique is by separation of variables. So when we get to Schrodinger's time-independent equation, by definition, the wave functions we're solving for are stationary. They don't have the time dependence. All right, the time dependence is in the separable part for the time. Okay, so here's the scoop. Remember when we solved for the infinite well? All right, we had some wave functions, and I forget what the wave functions are.
Square root 2 over a.
Okay, so let's do that. Yeah, thanks. So for 1D, so thanks, David. For 1D infinite well, we got solutions psi n of x. These are the stationary states for the infinite well. It was the square root of 2 over a, right?
Yeah.
Psi
N pi x.
n pi x over a, right?
Yeah.
Okay. And we got for n equals 1, 2, 3, 4, and so on. Now, for n equals 1, we call that the ground state. Let's call n equals 1 the ground state. All right, and we're going to call the n equals 1 ground state because it's the first non-zero solution. Everybody agree? So the ground state is the lowest non-zero solution that you can have for a particular quantum problem. Right? But if I start off with the ground state and I ask for what's lower than the ground state, what do I get?
Nothing.
You get 0. Okay? So that's how all of these problems go. All these problems are going to have the lowest state, and then once you start with the lowest state, when you go below that, you get nothing. All right? So check out this trick, right? So let's call the ground state, and this is a little confusing. So here, the ground state is n equals 1. All right? But in general, let's call the lowest non-zero stationary state the ground state equal ground, and let's define this as psi 0. All right, it's the lowest non-zero solution. Okay, let's look at the harmonic oscillator. Harmonic oscillator.
Wouldn't that always be n equals 1, or in most cases at least?
Let's see. Okay, let's find out. Okay. So let's say in our harmonic oscillator there is a lowest state. I just defined the lowest state as ground state. There is a ground state. And I'm going to call that psi 0 for the harmonic oscillator. Yeah?
Yep.
Okay. How about if I do this? A minus psi 0.
It equals 0.
It equals 0. All right? Because I'm lowering from the ground state to 0. That equals 0. All right? So now, let's use what this actually equals. So this is, I can rewrite this as 1 over the square root of 2 h bar m omega, and then in parentheses, it's going to be what? Plus ip plus m omega x times psi 0 equals 0. All right, multiply both sides by this, and then this is going to be I times minus I h bar partial with respect to x of psi 0 plus m omega x of psi 0 equals 0. So this is going to be, so you multiply this is going to be, this is going to be h bar partial psi 0 with respect to x equals minus m omega x psi 0. What do I have now? It's a differential equation. But can I solve this one? It's first order, and first order differential equations are kind of cupcake, right? So we started off with this very messy, look at this is a second order differential equation with an x squared. And after all that stuff we've gone through, we've got this. And can we solve this? How do we go about solving this? By the way, I can make these total derivatives again. This is a discussion we keep on having. But these are total derivatives. Can I solve that?
Yes, all you do is
Separate the variables again, or isolate them, however you want to say it. So it's going to be, let's see, it's going to be d psi 0 over psi 0 equals minus m omega x over h bar